Just a second to get situated. Okay, so I'm going to talk about histogram serialization. This was something I presented at pyhep.dev a couple of months ago, and it was almost complete, and I had a few remaining things that needed to be finished. Now it is finished and it's out. You can use it today, and I'll be showing you what it looks like, and now you can use it. So to get started, we have a family of histogram libraries. We have boost-histogram, which is a sort of the core library based on the C++ Boost library that does high performance histogramming in Python. Hist is a library that builds on top of that with extra features. And UHI is something I'll be talking about heavily today. This is a specification for histogram indexing. It's both a library as well as a specification. And it's meant to be an optional library, though you'll see with the serialization, it's a highly recommended optional library. And then there's other libraries, and these other libraries can interact because of UHI. So Pyroot, which you saw earlier in the conference, um, Uproot, Baby Yuta, Vistaprint, MPLHEP are some of the examples of libraries that implement at least some portions of UHI so that they can interact. So histograms are best viewed, I believe, as first-class objects in a language. That's the approach that Boost Histogram takes. And from Boost Histogram's side, a histogram is simply a collection of axes and a storage. So, for example, this is a 1D histogram where you put one axis in a histogram. The thing you store here is the storage. In this case, this accumulator could be it could be a double, it could be an integer, it could be a weighted value, which would be a couple of values. It could be, in histogram terms, it could be a mean, which would be similar to a profile in root, where you're storing, instead of storing the sum, you're storing the average communication. And you have zero or more axes. So in this case, we have one, and the axes describe how you convert between data coordinates and bin coordinates. And these can optionally have underflow and overflow. Here's a similar example with 2D where you can mix any of the different axes types, and you still get you get a 2D object out. So it's a lot like a NumPy array, except since you are building them out of axes and you have choices over the axes. You can do a regular axis, which has even binning. You could have axes with transforms, like a log transform here. You could have integer axes. You can have categorical axes, etc. And if you look at boost histogram, then it implements it this way, where you'd say import boost histogram. And you can create a histogram by just simply giving it a series of axes. Here we're giving it one axis, a regular axis, which is 10 bins starting from 0 and stopping at 1. And if you leave off the storage, then it's just a double by default. And here is how you could do indexing. So you can say you can use the bh.loc to convert from data coordinates. So here's 0.2 in data coordinates to 0.5 in data coordinates. And then you can sum over all of those. And so the return of this expression at the bottom will be the sum of the yellow bins you see on the plot. Hist builds on this, so it gives you some new options. So for example, this is what the constructor can look like in hist. It has this mechanism that's a little bit easier, especially if you have tab complete um, to write. And it has some shortcuts for how you can do various things. So in this case, instead of wrapping this in a bunch of extra parentheses and things, we can just add the letter J to the end, and that automatically tells you that that's data coordinates instead of bin numbers. So that's again 0.2 to 0.5 in data coordinates, sum over those. And there are many different axes types, regular binning, variable binning, where you get to pick um, the points. Um, The access performance of these is different. So you can also, for regular bins, you can also provide a transform, which will still give you the constant access, whereas variable binning, you have to look up inside of a list, a sorted list. So it's a login performance. Integer binning, integer category binning, and string category binning. There's some other examples. And then most of these also have options, like they could be circular. You can turn on and off overflow and underflow, and growing bins as well. So this is a comparison of boost histogram and boost histogram has a bunch of different core features. The um, it's really just it's a compiled code that sits on top of the boost histogram library. And it has supports histograms from 1 to 32 dimensions, many different axes types, different storages, multi-threaded support, and has the ability to manipulate filled histograms. And the hist adds things on top, so it's the same thing. It just inherits from boost histogram, but then it adds extra features. So new construction options like giving it an existing data, giving it a data frame to construct from, for example, has that quick construct I showed you before. All the axes can have names and labels, and the names can be used anywhere that you would normally access something by integer access. You can now access it by name. It has new methods like density and fill flattened. Fill flattened lets you put in an awkward array or other structures that need to be flattened and fill from them. It has various sort of advanced shortcuts like I showed you before with the complex numbers. It has built-in plotting helpers, so it's got pull plots and pie plots and various things like that. It supports this concept of a stack of histograms. So you can manipulate a histogram as a stack and some interval functions. So things like that. This is all part of a larger family. You can't always find everything you need within just those two libraries. What about Histoprint and MPLHEP? And in fact, we're integrating with MPLHEP and Histoprint for our plotting. And then other libraries like Uproot, Yoda. And so what we did is we introduced UHI, this set of standards that libraries can implement. And it's also itself a package. So the documentation has the standards listed, but it also has a set of helpers that packages can use if they want to. Generally, it's not meant to be a required runtime dependency. It is not a required runtime dependency of Boost Histogram. But it's just a simple Python-only library that's easy for anyone to use if they want. And so these are the things that it has. It was the letters actually originally stood for Unified Histogram Indexing, but it was expanded to be Unified Histogram Interface because it's now a collection of different things. So it describes this indexing. Libraries can implement indexing. And something that's new this year is we've added a new test framework that allows a library implementing indexing to then see if they pass a collection of tests that we provide. And you notice that Pyroot is now running those tests. We have sort of the advanced indexing. Currently, this is hist only, but these are the extra parts that hist implements. We have plotting, and quite a few libraries are also implementing this plotting protocol, which is it's a Python static protocol that you can implement. And if you implement it, then libraries like MPLHEP will be able to plot your histogram. This is how MPLHEP is able to plot uproot histograms without having to convert them to boost histogram or hist first. And this new serialization portion that I'll be talking about today. And some things like Pyroot and Baby Yoda have implemented some of these things, like using our test framework. This is a quick example of some of the things you can do with indexing. There's really a lot that you can do with indexing. You can index and get a single value, both from a bin index or from the data index. You can even combine them with plus and minus, underflows, overflows. You can do slices. You can do slices that are based on the index. If you put a dictionary in here, you can even put the index of the axis that you're trying to target. If this was hist, you can also put the string in here as well for the name. You can do a variety of different slices that return back either histograms, or if you have a For example, a sum that can sum over and do projections. And you can do this all per axis, so you can just chain this however you want. So you can sum over some axes, you can sum over ranges of some axes, you can keep the other axes intact, etc. You can also there's a rebinner, so you can rebin and do quite a bit. And this also works with settings, so you can set histograms with values or arrays, and there's sets of rules for setting an array based on the underflow and overflow. You can even handle that based on the size of the array that's coming in. So you can do all those sorts of things. And it's the syntax looks like NumPy if it can reduce to NumPy, but if it's something that does not work in NumPy, then we're allowed to add something for it to do with our indexing. Now, this is the new test framework, and this is useful for people writing an implementation. So this is something that the Pirate and Baby Yoda authors picked up and used. And so what we do is we provide this thing, this uhi.testing.indexing.indexing 1D, 2D, and 3D. And then you simply make a class that inherits from that. And you add a single method, this class method, make histogram. And if you support serialization, then it's actually really simple because we give you the serialized form of the histogram, and you just can take that serialized form and deserialize it. So this would be how you could do it for anything that supports serialization. So if you just call .get UHI, it will give you the UHI serialization form, which I'll talk about later. And you can and that will then give you histogram. Otherwise, you could just implement this yourself. You have the various values. As long as make histogram does return a histogram with the correct properties, the correct number of bins and things like that, then this will then run several dozen tests uh, on your uh, on your histogram. Um, and so for example, if you had Baby Yoda, you could put a Baby Yoda histogram here, and then make sure that would convert to Baby Yoda, and then it would test all Baby Yoda's 1D. And 2D, Baby Yoda does not support 3D, so you would just implement the 1D and 2D ones. If it makes it easier, I can remove the typing support just to show you this without the types, because this is really all that you need. This is implemented with unit test, and the reason we do that is because PyTest doesn't really support these sort of running tests that you've defined somewhere else because it doesn't rewrite the assert statements. So unit test is actually great for this, but you absolutely can run it with PyTest, and it will still give you all the nice output and everything. So this is one of the rare cases where it's actually better to implement something in unit test. Um, but we just have to do that once, the hard work for you once, and you just have to write a few lines to implement it, and then you have lots of tests defined for you that run separately. And now for serialization, this started as a two-part design. The this is a two-part design. We developed a schema that was independent of the storage format. That said, all right, this is how we define what each axis should be, etc. And then different backends like HDF5 and zip can implement the same can implement the schema. And I think one thing that was really useful here is we ended up splitting this up into a two-part design. There's a Python dictionary that gets produced or consumed by tools like boost-histogram. So boost-histogram has the ability to produce this Python dictionary that represents a serialized histogram. And then we provide a set of helpers, and these are implemented in UHI, that take a dictionary and then can write it to multiple different formats. And of course, the other direction as well. We have helpers for both directions. And this allows us to implement serialization once for the library that we're interested in, for example, boost-histogram. And then we can implement the various writers in UHI, and then other libraries who want to do this can just use UHI, produce the dictionary of the correct format, and then they support all the different formats that we support. We've currently implemented HDF5, zip, and JSON, and there's one of the main reasons for having several formats is that you can combine this with other information. For example, if you're storing some of your other stuff in HDF5, then you can go and store your histogram alongside. And there are different there are some drawbacks to each one. For example, HDF5 you cannot do from free-threaded Python because the HDF5 library doesn't have free-threaded wheels, which they should. Um, so there's different features and drawbacks of each. So HDF5 is structured, it's efficient, it's a great way to store data. You can put other data with it really easily. The zip format is has all the metadata in JSON, but the values are in binary files, so it's still fairly efficient. And again, you can combine it with other stuff in a zip file. And there's also a JSON format, which is really handy for small histograms testing. It's a great way to just store a histogram in a text file if it's small. Root may be added in the future. That was one of the original targets. Um, and there's some work going on for Azar backend, and I believe people have asked about Parquet format as well. For new format, there should have some reason to do it, but it's a fairly low overhead to add one. So here's an example of what the JSON looks like for a simple histogram. You have the histogram name, or you store it in a key, and then the schema describes what's inside of this key. Everyone should have a UHI schema set to 1 because that's our current version. And then you can optionally write in writer info. That is optional. You don't have to, but most writers like to add some information about themselves. So boost-histogram, for example, can add its version, and that's the one recommended key. And boost-histogram will write a little bit of extra information as well for different axes types and things. And then you have the list of axes. There's optional metadata and writer info fields for each of these. And then storage, and that's where the actual values get stored. And this is the main thing that's different. Say for the zip format, it would actually store this values array as a NumPy file instead of storing it right here. So this is what it would look like for a small simple histogram. So some of the design choices, these are true across all the different backends. They're always a collection of named histograms, so you can put multiple histograms in a file. And we didn't want to force you to do something at the top level of the file because we wanted to allow you to also store other information with it. The storage key contains the data of the histogram. The axes contains a list of the axes objects. Both the axes and the histogram itself have metadata and writer info. Metadata being user supplied metadata, and writer info being information from the backend tool that's writing it. And there's a limited set of information that we're allowed that you can put in there. Like I think we currently support floats, integers, strings, a few things like that. If somebody wants something else, then let us know. But it is a dictionary, so you can put as many of those things as you want. And we currently store integers, doubles, weights, means, and weighted means. So those are the storages that we support. And we have support for both dense and sparse histograms. So since boost-histogram itself does not support sparse histograms yet, at least the Python one doesn't, then UHI does provide helpers to convert between dense and sparse. So you can still take your boost-histogram that was filled densely, but if it's mostly sparse, you can convert it to sparse before storing it and save your space. And UHI provides helpers for that. And then across all the backends, including the ones we have now, really we just take this native format and we map it. The simplest mapping is the JSON, which is pretty much just pretty directly writes things from Python to JSON with just a few rules on converting arrays, but that's about it. So you're basically seeing when I show you an image like this, that is basically the Python format, except capital T, true and false, maybe if you wanted to make it look exactly like what it's stored in Python, and these are NumPy arrays. And then when you're putting this into data, you're allowed to redirect the data somewhere else or use the native structure, like a zip file would put it in a separate file and then give you a redirection string that tells you where to find it. And then we implement inside the UHI library. And if you produce the required structure, the UHI library can do it. There are limits, as I mentioned before, on what metadata is allowed. and arbitrary tool info is also allowed, but it's not never required to open the file. In fact, we also provide helpers to delete that information. That should never be required to open the file. But it can be used, for example, to improve the round trip performance for a library that knows a little bit more about, like, if it was circular, for example, um, then it could potentially store that information and then pull it back. Boost-histogram does do a few of those things. And then you use the native tool interface to serialize and unserialize. And that's important. That's actually the only thing we provide right now is this low-level interface. It's designed to to look like whatever the backend expects. So, for example, you'll see examples of each of these backends, but it is meant to be as flexible as possible. We are open to suggestions for high-level ideas for hist. So, if you want like a simple method or something in hist, we could add that. But this is the most flexible because it allows you to control things like you can easily control the zip compression or the where you put it in the file and things like that. So here's an example for JSON. And for JSON, if you want to read it, it would look like this. You would read in your file as data, and then you can run it through. And I'm using the string example here because it's easier, and you can also obviously not do the load s. You can do the load without the s and do a file object. But this I could do line by line. So we do JSON load s, we give data, and then we pass in this object hook, which is the Python JSON mechanism for customizing what it looks like to load JSON. And in uhi.io.json, we provide an object hook, and this really just makes sure that it handles I think really the only thing it's doing is it's making sure it loads those NumPy arrays correctly. Same thing with saving a JSON file. We just dump this back out to JSON, and again, we pass the default equals, and we have a uhi.io.json.default that you put here. And again, it's really just making sure that the NumPy arrays serialize and deserialize correctly, following the format. But this uses the native Python interface, and we just provide helpers in the standard way that Python expects. So you have complete flexibility here in how you would structure this. If you want to put this inside of a nested object or whatever, you can. HDF5 looks like this. You use the native HDF5. So this is the HDF5 PY library. And you open your file. And for each one of these, for each histogram you want to save, you make your own group for it. And this could be nested deeply inside your file, or it could be on the outside, or it could be wherever you want. But then we have a uhi.io.hdf5.write, which will then takes a group, which is here, in histogram, and it serializes it into that group. So again, you can put it wherever you want. Same thing for reading it back out. You just give it the location of the histogram as the HDF5 object, and it knows how to read that into a histogram. You get a histogram back out. And again, by histogram, what you get in and out here is the low-level representation. There is a protocol design, so if you give it a high-level implementation here for input, for the one on the top, then that will also be understood automatically because there is a protocol for that. There's a to-UHI method. For the way back, you are going to need to make sure you convert it to the histogram library of your choice. But both boost-histogram and hist have been updated to take this format, this raw UHI implementation, and understand it as a constructor. Zip looks pretty similar. There's a uhi.io.zip, and you give it the zip file, which you open yourself. You can control compression and all that sort of stuff. A name, and then a copy of the histogram. And I don't particularly remember why I did a full copy instead of just doing the histogram object itself, but I think that was for demonstration, or maybe that was an old bug that was in the first initial versions. The versions that support this, so you can try it out today. Boost Histogram 1.6.1 supports this. There were some bugs in 1.6.0, which I think might have been why there was a deep copy there. And then hist 2.9 and UHI 1 are the versions that were released that support all of this. There is documentation as well. Um, so if you go to the serialization page on UHI's uhi.readthedocs.io, then you'll see this page on serialization describing the format and the different backends and things like that. If you want to implement your own new format, then you just need to try to make a one-to-one mapping of this intermediate format to your native format and customize as much as you need to be natural in the native format. Like for HDF5, there's decisions on whether it should be you should make something a data set or a attribute. So those are decisions we had to make when implementing that format. You make sure you have the helpers in UHI for reading and writing. And then it needs to have documentation so that people know how to implement it, especially from a different language, and submit it. And ideally, there should be some advantage, some reason that you want to do this. Say you have a lot of data in parquet files and you want to put it with those, or for ZAR, maybe you'd want to take advantage of some of ZAR's like chunking features, etc. For C++, you should be able to implement this as well. Again, it's a spec that you can just follow. It's not completely clear where to put these helpers because of C++. You have to know C++ does have dependencies. So you would probably want to use high 5 for HDF5, for example. And you can't really implement that in the boost libraries. So you need to put that somewhere. Um, and similar things for zip files, you know how to read NumPy arrays, brute, etc. But you should definitely be able to implement this in C++. Even end users should be able to. For other libraries, everyone can use those helpers. I would rarely recommend using those helpers and just implement the intermediate format, which is not hard to do. And once you have the intermediate format, people can use the UHI implementation and you're basically done. And you support all the different formats for free based on what UHI does. Though, of course, you can implement these yourself. They're standards. There's a description of how you do this in HTML5, how you do this in JSON, etc. So you can implement them yourself as well. The JSON one specifically is extremely easy. And finally, to get involved, definitely try it out. Feel free to propose and work on a format if there's one that really matters to you. Um, I might be interested in working on this, helping with an extra format or two, maybe early next year. C++ and roots are still to-dos. It would be nice to have those again. Maybe C++ would just be an example of how to do it. And we should get some more examples into our test data. And maybe Upright Browser could gain some support for some of these formats. It might if these start showing up more, then we could maybe also allow Upright Browser to open, say, an HTML5 file or a zip file that has histograms in it and view them. With that, I think I have a couple minutes left for questions.